Hey, since some of you requested it, I'll do two examples, both of them using recursion, since I think that was probably the hardest topic. But I'll also cover dictionaries and strings in there too. So the first example with dictionaries, I'm going to be using a tree for the problem, and the goal of the problem is to start from the top of the tree and determine the longest path to the bottom of it. So if you start from this node, the longest path would be 3 because this has 1, 2, 3. There's 3 lines to get to the bottom of the tree. It wouldn't be 2 because 2 is not the longest path. So this would be it. And the goal of the program will be to calculate that given some tree in Python. I'll show some examples of trees and what their heights are. So this is a tree. It's just going to be a bunch of nodes, which are just these circles, connected by lines. So really you could think of it like a road system if you want. You start right here, and you travel down the road to this location, which you can then go to this location or this location. Or you can instead make a left turn and go to this place. Then your only option from here is to make a left turn to go to here, and then right turn to go to here. But the height of this tree is the longest stretch of road that you can take to get to the bottom, as in one of these nodes where you can go no further. So on this tree, how you'd calculate that is you maybe first look at the left children. And to get from right here to the bottom, you can take this way down to here, which in that case you only use 2 roads. Other way you could then go to here and then 4, in which case again you'd only take 2 roads. But you could also go to the right and go down to 2, down to 5, down to 6, which when you count the lines in between them is 3. So 3 is greater than 2, so that means the height of this tree would be 3. Here's another example. This tree would have, to determine the height, you could start from the left again, just like we did before. You go down to 1, go down to 2, go down to 3, go down to 4. Just imagine like traveling down to each of these. And so we count the lines to get down there. 1, 2, 3, 4. So there's at least one path where it takes 4 steps to get down to the bottom. But there's also another path, so we have to check that one to make sure that it's not longer than that, because we want the longest path. So you can go from 0 to 5, 5 to 6, which we count the lines, 1, 2. This path takes 2 steps to get to the bottom of the tree. But this path over here took 4. This path is longer, so we say that the height of the tree is 4. This last one is just a tree with a single node, which, if that's the case, this one's easy, because you're already at the bottom of the tree. You're starting at the bottom of the tree. That means this tree is a height of 0. So those are some examples of trees, and another thing I'd like to point out too is that to help for understanding this problem with recursion is that this itself, starting at 1 and down to 3 and 4, that is also a tree. Starting from 2 down to 5 and 6, that whole line part, like connection, is also a tree itself. So to determine the height of the overall tree, we could actually just say that it's equal to the greatest height of these children. So looking at 2, this tree has a height of 3. If you start at 2, ignore the connection right here, and actually I can just remake 2. And so this is exactly the same as that. So the height of this tree, using the same method as before, is just going to go 1, 2. So it takes 2 lines. So the height of this tree is 2. The height of this right here is 2. And we can do the same exact thing with this and just say that we check over here, then we're at the bottom, so then that took 1 step to get to the bottom. right here, took one step to get to the bottom, so the height of this tree is 1. So now we have a tree with a height of 2 and a height of 1. So we want the longest path, which means that if I want it to take longer to get to the bottom, I'm not going to want to use over here. I'm going to want to use this side because it's longer. So this would maybe seem like it's the height of this tree of 2, but there's an additional step we have to do, and that is we actually have to travel one additional stretch of road to get to this tree first. Once we get to here, we've already counted it. We know it takes 2 steps to get to the bottom. But we're starting right here, not right there. So that means we have to take this one stretch right there and then get to here. So that means the actual length we're traveling is 1 more than the height of this tree. Which the height of this tree is 2, then we add 1. That means 3. Since this had the greater height of the 2 children, the longest possible path you could take to get to the bottom would be going to the right, going down here and down there, which would take a length of 3, which, just like we counted before, is true. And we can do that with any of these other trees too, just the same. I isolate this, consider this its own tree, and this only has a height of 1, as we determined. It's pretty easy. So we compare that with this one, which this tree has a height of 3. 1, 2, 3, 3 line segments. So clearly we're going to want to travel down this path to get the longest path to the bottom. But once again, the length of the path is not 3, because we're not just traveling down here. We have to go from here to there, which means we have to travel this segment here, which means it actually has a height of 3 plus 1, which is 4. So from this, I think it should be clear that a pattern starts to emerge, like for an algorithm to determine the height, which I'll write that down and I'll make that equation more clear. So what I was trying to imply from analyzing the trees is this formula. The height of any tree is 1 plus the length of the longest path to the bottom, starting at one of the top point's children. Which this is exactly what we were doing before. So the height of this tree is, we look at these 2 children. We determine which one of them has the longest height, which we calculate the height of this one. This one, as we saw with the single tree, was actually just 0 because you're starting at the bottom. With this one, if you start here, to get to the bottom, you got to travel 1. Which means this one has a height of 1. Which 1's clearly greater than 0. So that means the height of this overall tree is actually 1 plus 1. So the height of this tree should be 2. So before we actually make the function that's going to implement the solution, as in calculating the height of a tree, we need a way of representing trees in Python, since they're not one of the base data types like lists, dictionaries, or numbers. So I'm going to use dictionaries to represent this tree, which you can easily change the tree. It's just I'll use this tree as an example. So this is how I implemented the tree. This represents the top node, node 0, and to the left of that, if you take the left path, you'll be at node 1. If you take the right path, you'll be at node 2, which I represented each node as a dictionary. So I've associated with left the node that you're traveling to on the left path, and I've associated with right the node that you're traveling to on the right path. Again, I do the same exact thing with node 2. So node 2, if you go left, you'll go to node 5. If you go right, there's nothing at the right, so I represent that with a blank string. So once you get to node 5, you can go right and go to node 6, but you can't go left. And at node 6, of course, both the left and right are blank because you're at the bottom of the tree, which means that you can't go anywhere from there. So this is how I'm representing it. You can represent any tree the same exact way, and here I'll show, because we're going to want to use this for the base case. This is for a single node tree. So this is a tree with just a single node, which just represents that other tree, where it's just one node and we said it had a height of 0. This tree here should have a height of 0. And you see you can't travel anywhere from there, so you should already be at the bottom. So that requires 0 steps to get to the bottom. So now I'll work on implementing the actual solution. So this is what I'm going to use for that. So I want to emphasize this in creating recursive solutions. The process goes like this. Make your function work for the base case. That'll be the first step. And then the second step is to assume your function works for every case smaller than the current one. I'll elaborate on that when we get to that step. But for now, I'm going to show how to do it for the base case. So like I said earlier, every tree is really just made up of a bunch of smaller trees, right? So if I'm at node 0, I go to node 1. Node 1 itself, I could use that as just the height, as just some other tree. And then, like I said there, we use that height to determine the height of the overall tree. So the one case that we know can work is if our tree is a single node. So every tree, like I said, is composed of individual parts, which means ultimately the smallest part of our tree is a single node. And we can determine if it's a single node by just using our get function for the dictionary. We have to get the left and we have to get the right. So this is just going to tell us what the left and right paths are. And like we said earlier, we know that it's just a single node if it's equal to that. And so if it's just that single empty string, we know that there is no farther I can go, which means starting on this node I've been given, I actually know that this node itself has a height of 0. So that's going to be my base case, because that is the smallest I can break down a tree into, a single node. So to test if that works, I'm going to push in our single node. And what this should give us 0 if it works correctly, which it does. So this tree has a height of 0, which is correct. We determined that earlier. So the next step is the recursive part. The recursive part is slightly harder, but it's not too much harder if you think about it like this. So okay, so to solve it, we're going to assume that we're trying to find the height of a tree with a height of h. We want this function to output h, because h is the actual height of the tree. So we're going to assume that our function can correctly calculate the heights of any tree with a height smaller than h. So for example, if h is 10, we're going to assume our function is correctly able to calculate the height for a tree with a height 9, or a tree with a height 8, tree with a height 7, tree with a height 6, all the way down to a tree with height 0. And so, assuming that works, we're going to use that function output to determine the current height of our tree. But this all hinges on assuming that our function handles those other cases correctly. So, like we said earlier, we're going to want to find the longest path, the child with the longest path. So first I need to make sure my tree even has both left and right children. So if the tree has a left child, or well, we want this not to be equal to the blank, because if it has a left child, we already said that if it doesn't have a left child, it's going to be a blank, and if it doesn't have a right child, it's going to have a blank right there. So the left height is going to then be, this tree is going to be smaller than our current tree, right? Because we don't have to travel all the way to the top. We're one node deeper. So instead, on this one right here, we're not starting at node 0 maybe, we're starting at node 1, because that's our left one. This tree cannot be as large as the overall tree, because it's only a part of the tree. So that means we can assume our function works. So I'm going to give it this. So this is going to pass to it So this is first off going to get the left child, and it's going to determine the height of the left child, as in the longest path you can take starting at that left child to get to the bottom. So then all we're going to do is the same exact thing for the right child. Once again, we have to make sure that right child even does exist. We don't know if it has a right child or not, and our function could break if we don't check this. So, yeah, exactly the same. So now we can assume that, because like as before, if this wasn't clear, the right child has a smaller height. So again, we're assuming our function works correctly. So we're assuming that this then will correctly calculate the correct left child height and the correct right child height. Which, if we look back at the formula from before, then if we find the the longest path of these two, which I'm just going to use the maximum function, but like if on the test, like maybe this isn't allowed, the maximum function, you can easily make your own maximum function. It's not hard. So this is going to get the maximum, the longest path out of these two. So now right here we have the longest path, which if you look at the formula, that means our height of our tree should just be one more than that longest path. Which means this should be correct. So it does sound maybe kind of strange, the strategy to assume that your function works for everything smaller. But if you know your function works for the base case, which we tested it, we know our function does work for the base case, then if you assume it works for everything smaller than the given test, then that means your function will work if it's true that given that the function works for things smaller, it will work for the current one. I can show this better in a second video. I'll also attach kind of the idea behind this. It's called mathematical induction, and you'll be covered more in 203, but that's the actual understanding behind it. But if you don't want to actually learn why it works, you can just do exactly this strategy. So, correct base case, then assume function works for smaller versions of our current input. And then, knowing that, use that information and relate that the output of the function for smaller inputs to the current inputs, which we did exactly that here. We related that by saying it's the maximum of the output of the function for the left child and the right child plus 1, which we can test it now. So earlier we deduced that that tree had a height of 3, I think. Which, yep, that tree has a height of 3. So that means when I plug in node 0, telling it to start at node 0, this thing should return 3 to me. Oh, okay. I should have set default values of these because not every node's going to have a left child or maybe not a right child. So left height and right height are actually undefined in those cases. So by default, we're going to set them equal to 0. Which, this won't break anything. It's just, if they do have it, they'll be correctly updated. If they don't, then since the height of a tree can never be smaller than 0, the one that's non-zero will clearly be the maximum and it will work. And now it should output it correctly. Yes, a height of 3. So this function then does work. We can test it with the other ones too. I'll let you do that, because the function should work here. But the nice part about this is that Recursion allows us to write this thing in a really small and compact way. You could even do this using loops. It's possible as well. It just might get more convoluted. This is just the more natural way.